Hello everyone, welcome back to another video lecture. In this video lecture, we'll see a problem on strain energy. Right? In the previous video lecture, we understand what is the concept of strain energy and what are the loading, gradually applied load, suddenly applied load and impact load on a material, okay, on a member or a body. So in this lecture we'll try to do some problems on strain energy. Let us see the question first. A steel bar of 50 mm into 50 mm in section and 3 meters in length is subjected to an axial pull. That means tensile load is applied on the bar of 150 kilonewton. Calculate strain energy stored in the bar. So we have to calculate strain energy which is stored in the bar when axial pull is applied, axial pull of 140 kilonewton, right? Also find extension of the bar. In the question is E value is given, that is 200 gigapascal, right? 200 gigapascal. Once again I will repeat the question. A steel bar of 50 mm into 50 mm, this is a cross section, and 3 meters long is subjected to an axial pull of 140 kilonewton. Calculate the strain energy stored in the bar and also calculate or find extension of the bar, that means change in length. When axial load is applied, we need to find out the extension, how much the rod or a bar is extended. Let us try to draw. So this is a cross section and it is almost 3 meters in length, right? 3 meters, and the cross section is 50 mm into 50 mm, right? So we have volume here. Let us write the given data. So what type of load? So it is gradually applied load, because if you apply a load, axial load on a UTM, that is universal testing machine, it will apply step by step. That means this kind of loading is known as gradually applied load. The load P will increase step by step or gradually. So in the question it is given 140 kilonewton, right? So the type of load is gradually applied load, applied load, that is, let us 3 meters length, convert it into mm, it will become 3000 mm. P is a load, that is 140 kilonewton. If you convert into newtons, that will be 140 into 10 to the power of 3 Newton, right? So this is a given data. Anything else? And let us write here. First we need to find U, that is strain energy. So we have to find this. Next we have to find the extension, that is, let's say delta. L is the extension, that is change in length. U is the strain energy and change in length. Let us see. So the solution for this, for gradually applied load, we know the formula is very simple, that is stress equals to load upon area. Right? What is stress? Denoted by sigma, that is load upon area. 140 into 10 to the power of 3 upon 50 into 50. Put this on your calci, as to sigma equals to 50 Newton per mm square, right? So this will be the stress. Now we'll find out the first given task, that is strain energy, right? And we know the formula we derived in the last previous video lecture, that is U equals to sigma square upon 2E multiplied by volume, right? If you didn't watch the video, please go back and watch it. The strain energy, we derived the formula for strain energy. So put the values here, that is, you can write here, right? U equals to 56, yeah, here it's 56, right? Sorry, it's 56 to 10 to whole square and 2 into 200 into 10 to the power of 3. E is given in gigapascal, so 1 gigapascal is nothing but 10 to the power of 3 Newton per mm square, right? Into volume, we know that 50 into 50 into 3000. Put this value in calci and say me the answer. What it will be? It will be 144 Newton meter, right? So it will come in 144 into 10 to the power of 3 Newton per mm. I'm just converting the mm into meters. So the 10 to the power of 3 will gone, then we'll got in meters, right? Next we'll find out the deflection. Okay, so we know the deflection or extension, we can call it as a deflection or change in length. So deflection is given delta L equals to sigma L upon Young's modulus, right? Put the values here. Delta L equals to sigma, we got sigma, that is 56 into L. What is the length? That is 3000 mm is the length, and E we know that 200 into 10 to the power of 3. So now we'll get the change in length, that is 0.84 mm, right? So this is how you can find out the extension in a bar, and also you can find out the strain energy by using this formula, that is U equals to sigma square upon 2E into volume, right? And the formula for deflection or extension in the bar is delta L equals to sigma multiplied by length upon Young's modulus, right? We'll see another problem. A mild steel plate is 400 mm long and 200 mm wide and 50 mm thick. A mild steel plate is 400 mm long and 200 mm wide and 50 mm thick. Is subjected to gradually applied load, right? To a gradually applied load of 1200 kilonewtons. Calculate the following. First, we have to find the proof resilience. Second one, we need to find modulus of resilience, and the third one is elongation, right? First, we need to find the proof resilience and modulus of resilience and elongation. Let's see the given data first. So what type of loading is this? So it is given in the question, it is subjected to gradual loading. So it is gradually applied load, right? Applied load. So it is gradual applied load. Let us try to draw the cross section. So this is a long length with long 200 meters long, and the width is 50. Let us draw this. So it's a mild steel plate, and this thickness is 50 mm and the length is about 400 mm and the width is 200 mm. Okay, so let us try to solve the given points, that is proof resilience. So first we'll find out the stress. Sigma equals to, for gradual applied load, it will be P upon A, that will be 12,000 kilonewton, that convert into newtons, it will be 10 to the power of 3 upon 200, that is cross sectional area, 200 into 50, right? So put the value on calci and the answer will be 120 Newton per mm square. Right, we got the stress. Next we'll find out the proof, resilience. So U equals to, we know the formula for proof resilience, that is U equals to sigma upon 2E multiplied by V. Right. So we know sigma now, that is stress, is 120. So put the values 120, so whole square. So 120 square upon 2 into 200 into 10 to the power of 3. Right. So E value is 200 into 10 to the power of 3 into the volume will be 200 into 50 into the length is 400 mm. So put the values here, please see me the answer, that is 144 into 10 to the power of 3 Newton per mm. So that is the units for strain energy, that is Newton per mm. So U equals to 140 Newton per meter. If I remove this, if I convert into mm into meters, it will be 140 Newton per meter. Next we'll try to find out the modulus of resilience. Modulus of resilience, that is, the expression is given by sigma star, like sigma star square upon 2E. So you can denote with any other thing, but it will be, put the values here. For modulus of rigidity I am giving sigma star, and normal modulus proof resilience I am giving sigma, and for modulus of resilience I am giving sigma star, that is 120 square upon 2 into 200 into 10 to the power of 3. So 0.036 Newton per mm square. Right. Now we'll find out the elongation. So that is nothing but deflection. Now we'll find out the deflection is given by delta L equals to sigma multiplied by L upon Young's modulus. Right. So put the values. Delta L equals to 120 into, what is the length of the bar, that is 400 upon Young's modulus 200 into 10 to the power of 3. So what is the answer? Delta L, that is deflection, or you can call it as elongation or extension. So delta L, we got the value here, that is 0.24. Please, if I am wrong, correct me. Right, 0.24 mm. So the bar is extended 0.2 mm. So if I try to draw here, Wow, it's perfect. So the width is 200 and it is applied gradually, a pull kind of load, right? And the length is 400, that is the original length. And how much it is elongated? It is elongated a little bit, that is 0.24 mm, right? So thickness is given, that is 50 mm, right? This is how you can find out modulus of resilience, proof resilience, as well as deflection. So that's it for today's class. Hope you enjoy the problems. In next class, we'll see with a new topic. Till then, don't forget to like, share, subscribe. Take care of yourself.